Hello there, fellow cosmic voyagers or perhaps soon-to-be dreamers. Welcome. Settle in. Get comfortable as one can be when contemplating the rather loud, occasionally catastrophic and undeniably expensive symphony of human ambition reaching for the stars. Tonight, we're not just gazing at the pretty, twinkling lights, oh no. We're tuning our weary minds to the thunderous overture of our species' relentless, sometimes reckless, desire to escape this perfectly adequate, if somewhat overpopulated rock. We're about to embark on a sleepy history, a gently ironic exploration of the game-changing technologies in aerospace, the ingenious contraptions and brilliant blunders that have quite literally launched us into the void. Think of it as a lullaby scored by explosions, a bedtime story whispered over the roar of engines powerful enough to tear themselves, and occasionally their launch pads, into very small, very expensive pieces. We're diving into the deep end of the cosmic pool, where dreams are forged in incandescent fire and the profound silence of space is only occasionally punctuated by the ping of a micrometeoroid against a fragile hull, or perhaps the slightly panicked, muffled cursing of an astronaut who's just dropped a particularly important spanner. It's a journey of breathtaking achievement, of course, but also one littered with, let's call them, learning opportunities that often came with a rather steep price tag and a few singed eyebrows. Tonight, we begin our sleepy symphony of space conquest, where those celestial dreams are indeed forged in the heart of controlled detonations, and the cosmic silence, that vast, indifferent quietude, is sometimes shattered by rather large and frankly eye-wateringly expensive bangs. It's a tale of how we, tiny, fragile beings, decided that clinging to the surface of our planet just wasn't quite challenging enough. No, we had to aim higher, further, into places where the vacuum would happily boil our blood and the radiation would gently toast our DNA. What could possibly go wrong? So breathe deeply now. Let the day's accumulated anxieties, those little terrestrial concerns about deadlines and burnt toast and that awkward thing you said in the meeting, just drift away. They seem rather quaint, don't they, when compared to the monumental task of, say, preventing a multi-ton canister of highly volatile chemicals from becoming an unscheduled firework display? Allow your shoulders to soften, your jaw to unclench. We're going on a mind journey, a safe haven where we can marvel at human ingenuity, chuckle quietly at its occasional spectacular hubris, and perhaps even find a strange sort of comfort in the grand, absurd theater of it all. Imagine, if you will, the world before these leaps. A world bound by gravity, where the stars were just distant, untouchable diamonds scattered across a velvet cloth. The dream of flight was ancient, of course, depicted in myths of winged gods and feathered contraptions. But space? Space was the realm of philosophers, poets, and perhaps a few too many late-night cheese-induced visions. It was impossibly far, impossibly hostile. The idea of sending a person, a delicate, air-breathing, water-dependent person, up there? Pure fantasy. Like trying to teach a goldfish to ride a bicycle. Uphill. In a hailstorm. Yet, something in our curious, restless primate brains couldn't leave it alone. That silver disk of the moon hanging there taunting us. Those pinpricks of light hinting at, what? Other worlds? Other possibilities? Or just a whole lot of empty, cold, dark nothingness, which, to be fair, is a statistically significant portion of what's actually out there. But details. The dream persisted. And so, the overture begins. Not with a gentle sigh, but with the scratch of chalk on a blackboard, the frantic scribbling of equations, the smell of solder and ozone in makeshift labs. It begins with tinkerers, visionaries, and a few individuals who were probably considered charmingly eccentric by their more grounded contemporaries. People who looked at gunpowder not as a way to make loud noises on festive occasions, but as a potential push. A way to escape the relentless downward pull of everything. The early attempts were, shall we say, spirited. Imagine the scene. A hopeful inventor, a cobbled-together tube packed with something that fizzes and pops. A nervous crowd standing at what they hope is a safe distance. Sometimes, a satisfying whoosh and a small object briefly defying gravity. More often, perhaps, a disappointing fizzle, a rather loud bang followed by the distinct smell of failure and burnt grass, and the quiet dispersal of onlookers trying very hard not to make eye contact with the singed, dejected inventor. It's the cosmic equivalent of learning to walk, really. Lots of falling down. Lots of bumps and bruises. Except here, the bumps could vaporize a small shed. This symphony we're exploring tonight, it's conducted by these technologies. Each one a movement, a crescendo of new understanding, a sudden shift in what was deemed possible. From the first sputtering liquid fuel engines, those glorified drainpipes belching smoke and fury, to the silent, thinking minds of artificial intelligence that will one day, perhaps, guide our descendants to stars we can currently only dream of. It's a narrative of problem solving on an epic scale. Problem: Earth's gravity is annoyingly persistent. Solution: build a bigger fire. Problem: space is big, dark, and doesn't come with road signs. Solution: invent a brain in a box that knows where it's going, hopefully. We'll touch upon the sheer, terrifying power required, the delicate precision needed to thread a cosmic needle millions of miles away. We'll marvel at the ambition, the audacity of it. And yes, we'll also acknowledge the fine print, the bits they don't always put in the glossy brochures. The bone-jarring vibrations, the crushing G-forces, the profound isolation, the constant, gnawing awareness that you are a very small, soft thing suspended in an environment that is actively, if impersonally, trying to kill you in about 17 different ways simultaneously. Relaxing, isn't it? But here, in this space between wakefulness and sleep, we can appreciate it all with a sense of detached wonder, perhaps even a wry smile. The universe, in its infinite, cold majesty, doesn't much care for our frantic scrabblings. It was here long before us. It will be here long after our most ambitious rockets have rusted into cosmic dust. And there's a peculiar sort of peace in that, isn't there? A release from the burden of ultimate significance. We're just curious motes, briefly flaring with bright ideas before winking out. But oh, the sparks we make in that brief moment. The glorious, improbable, occasionally self-immolating sparks. So let your mind drift. Let the sounds of your room fade. We are embarking not on a spacecraft of metal and wire, but on a vessel of thought, gliding through the story of how we reached for the heavens, sometimes grabbed a handful of stars, and sometimes just got a face full of interstellar dust and cosmic irony. The overture is playing a grand, slightly chaotic, but undeniably human composition. And the journey has just begun. And as we drift further into this sleepy overture, our vessel of thought glides gently back, not to the gleaming launch pads of Cape Canaveral, not yet, but to quieter, perhaps slightly muddier fields, to workshops filled with the scent of chemicals and the insistent buzz of solitary obsession. For before the towering giants like the Saturn V could even be dreamt of, there were pioneers, true originals, wrestling with the fundamental problem of getting anything at all, to go up and stay up without it immediately deciding that down was a much more comfortable, if less ambitious, direction. We're talking about the dawn of liquid fuel rocketry, the moment when the dream of spaceflight graduated from enthusiastic, if somewhat unreliable, fireworks to something that hinted at actual control, actual purpose. Let's gently land our thoughts near one Robert Goddard, a name perhaps not as universally sung as Armstrong or Gagarin, but one without whom their famous boots would have remained firmly planted on terrestrial soil, probably complaining about the price of bread or the weather like the rest of us. Goddard, a quiet, unassuming physics professor, had a rather explosive hobby. While his contemporaries were perhaps concerned with the intricacies of quantum mechanics or the proper brewing of tea, Goddard was out in the fields of Auburn, Massachusetts, launching what can only be described, with the benefit of hindsight and a touch of affection, as glorified drainpipes. Picture it, a spindly, awkward contraption, often no taller than a man, looking less like a vehicle of destiny and more like a plumbing experiment gone rogue. These early liquid fuel rockets, his children as he sometimes called them, were a far cry from the sleek, powerful machines we envision today. The fuel? Often a volatile cocktail of gasoline and liquid oxygen. Substances that, when not carefully chaperoned, have a distinct tendency to disagree with each other in a rather dramatic and incandescent fashion. The engineering was groundbreaking, of course, but to the casual observer of the time, it might have looked less like the dawn of the space age and more like a man with a worrying pyrotechnic fixation. There were failures, naturally. Many failures. Rockets that stubbornly refused to leave the ground, rockets that cartwheeled spectacularly, rockets that achieved impressive altitudes only to return to Earth with the aerodynamic grace of a hurled brick. One can only imagine the polite, strained smiles of the local townsfolk, perhaps muttering about that Professor Goddard and his noisy contraptions again, while discreetly checking their home insurance policies. Before their advent, the script often reads, the dream of spaceflight was purely theoretical. Solid fuel rockets had limited thrust and poor control. And that's the polite version. Solid fuel rockets, the kind that power your average firework or a very large, unguided missile, are essentially a controlled explosion in a tube. Once you light the fuse, you're pretty much committed. There's no throttling back, no steering committee, just a rapid, often unpredictable conversion of chemical energy into enthusiastic upward motion, followed by an equally enthusiastic, and often equally unpredictable, return journey. Fine for scaring pigeons or delivering a hefty payload to a general, pre-agreed vicinity. Not so fine if you're hoping to, say, achieve a stable orbit or gently kiss the surface of another celestial body without pulverizing it, and yourself into a fine, regrettable powder. This is where Goddard, and others like Konstantin Tsiolkovsky in Russia and Hermann Oberth in Germany, names whispered in the hallowed halls of rocket science like incantations, truly became the godfathers of liquid thrust. The breakthrough was this. By using liquid propellants, typically a fuel and an oxidizer kept in separate tanks and then precisely mixed and ignited in a combustion chamber, you could, in theory, control the burn. You could throttle the engine up or down. You could even, miracle of miracles, stop it and restart it. This was revolutionary. This was the key. This was the difference between a firecracker and a finely tuned instrument. Imagine Goddard, hunched over his designs, meticulously calculating flow rates, combustion pressures, nozzle shapes. The sheer, stubborn persistence required. He faced skepticism, ridicule, and a chronic lack of funding. His work was often dismissed as the fanciful daydreaming of an impractical academic. The New York Times famously scoffed at his ideas in 1920, declaring that rockets couldn't work in the vacuum of space because they'd have nothing to push against, a delightful misunderstanding of Newton's third law that the paper would formally, and rather sheepishly, retract on the eve of the Apollo 11 mission, nearly half a century later. It's a comforting thought, isn't it? Even esteemed newspapers can have a cosmic brain fart now and then. Makes one feel a bit better about forgetting where one left the car keys. His first successful liquid-fueled rocket flight, on March 16, 1926, was hardly a spectacle to rival future launches. The rocket, nicknamed Nell, rose a modest 41 feet, flew for 2.5 seconds, and landed in a cabbage patch 184 feet away. Not exactly punching a hole in the stratosphere. But in those 2.5 seconds, in that sputtering arc through the Massachusetts sky, the space age had, quite literally, taken flight. It was proof of concept. It was the Wright brothers' first hop at Kitty Hawk, but for the vertical dimension, and with a significantly higher chance of unscheduled explosions. These early rockets were less Apollo, the majestic chariots of the gods, and more akin to hope it doesn't land on the neighbor's petunias, or perhaps more accurately, hope the cabbage farmer has a good sense of humor. The journey from these tentative, sputtering ascents to the thundering behemoths that would later carry humanity to the moon was long, arduous, and punctuated by many, many more bangs, some triumphant, some tragic. The work of these pioneers, often done in relative isolation, with shoestring budgets and the constant shadow of failure, laid the invisible foundations. They were figuring out the incredibly complex dance of fluid dynamics, thermodynamics, and material science, often through painful trial and error. Each failed engine, each crumpled rocket, was a lesson learned, a data point in the slow, agonizing crawl towards the stars. It's a testament to human stubbornness, really. The universe presents a problem, say an inconveniently strong gravitational field, and we, bless our cotton socks, just keep tinkering with bigger and better drainpipes until we find one that shouts back loudly enough. So, as you feel yourself drifting, picture Goddard, a solitary figure in a field, gazing skyward after a puff of smoke and a fleeting ascent. There's a quiet dignity in that image, a profound embodiment of human curiosity. It's not glamorous. It's not bathed in the spotlight of global television. It's just one mind wrestling with the laws of physics, fueled by a dream that most people probably thought was utterly bonkers. And yet, from those humble, glorified drainpipes, came the roar that would eventually shake the world. A gentle reminder that even the grandest cosmic journeys often begin with the smallest, most uncertain, and occasionally cabbage patch landing steps. Let that thought cradle you as you drift further and further away from the day's concerns, into the quiet, starlit fields of your own mind. And so, from those early, almost comically fragile drainpipes, the technology of liquid-fueled rockets began its inexorable, thundering evolution. Decades of relentless research, fueled by national pride, geopolitical anxieties, and yes, the sheer, unadulterated scientific curiosity of thousands of brilliant minds, culminated in machines of almost unimaginable power. We now drift forward, leaving the cabbage patches of Massachusetts far behind, our sleepy thoughts drawn towards the humid, expectant air of Florida in the late 1960s. Here, rising from the coastal plains like a metallic titan, stood the Saturn V. If Goddard's early rockets were hesitant whispers, the Saturn V was an earth-shattering, window-rattling, deity-invoking bellow. This wasn't just a rocket, it was a monument to human ambition, a 363-foot-tall skyscraper of propellants, engines, and exquisitely complex plumbing, all designed for one singular, audacious purpose: to lob a tiny, fragile capsule containing 3 human beings towards another world, a quarter of a million miles away and then ideally bring them back in one piece. No pressure then. Riding the biggest firework ever made, that's precisely what the Apollo astronauts did. It was a symphony of controlled destruction, a meticulously choreographed inferno, all just to wave a rather expensive and fleeting hello to the moon, and perhaps to make us pause and contemplate the cosmic fuel bill for such a brief, if historically monumental, interplanetary jaunt. Imagine the scene on launch day. The countdown, each number echoing with decades of work, hope, and no small amount of nail-biting anxiety. The final seconds measured not just in time, but in the palpitations of a global audience holding its collective breath. And then ignition. The 5 F1 engines of the Saturn V's first stage, each one more powerful than any single engine ever built before, erupting into life with a sound that wasn't merely heard, but felt, a visceral, ground-shaking concussion that ripped through the air for miles around. It was, quite literally, the power of a small nation unleashed in a single vertical column of fire and fury. 7.5 million pounds of thrust. Think about that. It's the equivalent of roughly 160 million horsepower. Your family car, bless its efficient little engine, probably has around 150. This was not a gentle liftoff. It was an eviction notice served to gravity with extreme prejudice. The achievements these engines enabled are, of course, legendary. They paved the way for orbital flights, yes, but their crowning glory was undeniably the Apollo program. Landing humans on the moon, that stark, beautiful, and utterly lifeless desolation, was more than just a technological triumph. It was a profound moment in the story of life on Earth. For a brief, fleeting instant, we were a two-planet species, albeit with a very tenuous and temporary foothold on the second one. The Saturn V was the workhorse, the muscle, the sheer brute force that made it possible. It launched the Skylab space station, America's first. It sent probes like Pioneer and Voyager on their one-way journeys into the cosmic deep, carrying messages from a tiny, curious species to whomever, or whatever, might find them in the eons to come. Talk about a long-shot message in a bottle. But let's peel back the heroic sheen for a moment, as we are wont to do in these sleepy, honest explorations. The Saturn V was an incredible machine, yes, but it was also an astonishingly complex, borderline terrifying, and mind-bogglingly expensive one. Each launch consumed fuel at a rate that would make an oil sheik blush. The first stage alone guzzled about 15 tons of kerosene and liquid oxygen per second. That's like vaporizing a small fleet of delivery trucks every tick of the clock. The engineering was a marvel of precision, but it was also operating at the very edge of what was physically possible. Thousands of welds, miles of wiring, intricate turbopumps spinning faster than a dentist's drill, handling cryogenic fluids at temperatures that would flash freeze a brass monkey in a nanosecond. The number of things that could have gone catastrophically wrong is, frankly, terrifying to contemplate. It's a miracle any of them ever got off the ground, let alone performed their celestial ballet with such repeated, stunning success. And for the astronauts perched precariously atop this controlled explosion? Well, riding the lightning is a common descriptor, and it's not far off. The vibrations were intense, shaking them like dice in a cup. The G-forces pressed them into their couches, making every breath a conscious effort. They were, in essence, strapped to the warhead of the most powerful non-nuclear device ever created by humanity. Romantic, isn't it? Makes that slightly bumpy landing on your last commercial flight seem positively serene by comparison. One can only imagine the internal monologue. Please don't explode, please, for the love of all that is holy, don't explode. Oh look, the Earth is getting smaller. Neat. The sleepy angle, as our notes suggest, is indeed the unleashed potential power, the fire that carried humanity to the stars. But it's also a meditation on the sheer, almost absurd, effort involved. All that fire, all that noise, all that astonishing expenditure of resources and brainpower, to send a handful of people on a camping trip to a dusty, airless rock. It's both magnificent and slightly bonkers, isn't it? It speaks to a fundamental human drive, that restless urge to see what's over the next hill, even if that hill is a quarter of a million miles away and located in a hard vacuum. The Saturn V, of course, was a single-use vehicle. Each glorious launch ended with its stages becoming very expensive, very well-engineered pieces of space or ocean junk. The economics were, shall we say, unsustainable for routine access to space. It was the pinnacle of a certain kind of thinking. Build it big, build it powerful, use it once and hope for the best. It got us to the moon, a feat that still resonates with awe and wonder. But it also highlighted the need for something different. Something, perhaps, a little less like a glorious, one-off cathedral of fire and a little more like a reusable work truck. So, as you let your mind float on the dying echoes of that Saturn V's roar, that monumental exhalation of human will, consider the sheer audacity, the beautiful, terrible power, the stark realization that our first tentative steps off this planet were taken on the back of a barely tamed inferno. It's a humbling thought, and perhaps in its own way, a profoundly relaxing one. The universe is full of immense, indifferent power. For a brief moment, we learned to harness a tiny fraction of it, enough to touch another world. And then we had to figure out what to do next. The silence after the roar is where the next chapter begins, and where your journey into deeper, more peaceful sleep can continue. As the thunder of the Saturn V fades into the vast, echoing silence of space, our thoughts drift from the sheer brute force of liquid fuel engines to something altogether more subtle, yet equally revolutionary. For once you've unleashed that monumental fire and pointed your fragile craft vaguely in the direction of up, a rather pressing question arises: how on Earth, or more accurately, how off Earth, do you know where you are, where you're going, and how to get there without accidentally performing an unscheduled lithobraking maneuver on the far side of the moon, or worse, missing your celestial appointment altogether and becoming a rather lonely and very permanent human satellite of the sun? This, my sleepy friends, is where the quiet genius of inertial guidance systems and the nascent power of aerospace computers enter our story. Imagine yourself, if you will, an astronaut in the Apollo era. You are encased in a metal can hurtling through the inky black at speeds that defy earthly comprehension. Outside your tiny window, there are no roads, no signposts, no friendly gas station attendants to ask for directions. Just the terrifying, beautiful, and utterly indifferent tapestry of the cosmos. Relying on a sextant and a slide rule, as mariners of old did, might be romantic, but it's also a recipe for becoming a permanent exhibit in the Museum of Lost Cosmic Explorers. No, for this journey you need something more: an unwavering, unblinking, and astonishingly precise artificial brain and senses. You need to trust your life, and indeed the monumental investment of a nation's pride and treasure, to a box of wires, spinning gyroscopes, and patiently blinking lights, as it diligently calculates your lonely, silent path through an uncaring, infinite void. Before their advent, we're told, navigating in space was extremely difficult, relying on complex and error-prone manual calculations. This is a wonderfully understated way of saying it was a bloody nightmare. Early space flights were often ballistic, like a well-aimed cannonball. You point, you shoot, you hope your maths was good. For anything more complex, like rendezvousing with another spacecraft or navigating the gravitational tap dance required to enter lunar orbit, manual calculations were simply too slow, too prone to human error. A misplaced decimal point, a moment of distraction, and your lunar lander becomes a lunar impactor. Not the legacy most astronauts aspire to. The breakthrough came with the development of inertial navigation systems, INS. At their heart are gyroscopes, those fascinating spinning tops that resist changes to their orientation, and accelerometers, which measure changes in velocity. By meticulously tracking every tiny twist, turn, push, and shove the spacecraft experiences, from the moment of launch, the INS can continuously calculate the craft's position, orientation, and velocity, all without needing any external references like stars or radio signals from Earth. It's like being blindfolded in a dark room but knowing exactly where you are and which way you're facing simply by remembering every step and stumble you've taken. Except this room is millions of miles wide and a stumble can be terminal. And then there was the computer. The Apollo Guidance Computer, AGC, is a legend in its own right. In an era when computers routinely filled entire rooms and guzzled power like thirsty elephants, the AGC was a marvel of miniaturization, weighing in at a svelte 70 pounds and occupying about a cubic foot of space. Its processing power? Roughly equivalent to a modern digital wristwatch or perhaps a particularly ambitious toaster. Its memory? A mere 72 kilobytes of read-only memory, those famous rope core memories, woven by hand by skilled textile workers, a wonderfully anachronistic detail, and 4 kilobytes of erasable memory. Your smartphone laughs at such paltry numbers. It probably uses more processing power to decide which cat video to show you next. Yet, this primitive computer, programmed with an elegance and efficiency born of extreme necessity, performed miracles. It guided the colossal Saturn V through its ascent. It managed the intricate rendezvous and docking maneuvers. It controlled the descent of the lunar module to the moon's surface, famously saving the Apollo 11 landing when its processing capacity was overwhelmed by spurious data from a misconfigured radar switch. Neil Armstrong, cool as a cosmic cucumber, had to take semi-manual control, but it was the AGC that provided the critical data, the digital co-pilot that kept them from becoming a new crater named Tranquility Base. Oops. The achievements are undeniable. These systems enabled precise autonomous flights to the moon and other planets, ensuring astronaut safety, or at least greatly improving the odds. They allowed for missions of a complexity that would have been unthinkable just a decade prior. The silent, tireless calculations of these electronic brains were the invisible threads holding these audacious missions together. They were, in a very real sense, the ghost in the machine's cockpit, an extension of human intellect projected across the void. The sleepy angle here is the intelligent brain guiding through the vast cosmos, the astonishing precision of machines. And there is a strange comfort in that, isn't there? To imagine that intricate dance of numbers, that relentless logical progression, unfolding silently while the human occupants perhaps catch a moment of uneasy sleep, or gaze in awe at the receding Earth. It's a testament to our ability to create systems that can, in some narrow but critical ways, outperform our own fallible senses and calculations. But let's not get too dewy-eyed. Entrusting your existence to a 1960s computer, however brilliant, also carries a certain existential frisson. Imagine the software update process. Houston, we have a problem. The computer thinks we're a washing machine on the spin cycle and is attempting to jettison the detergent dispenser, which appears to be me. Or the sheer terror of a system crash when you're halfway to Mars. There's no celestial IT support to call. You can't just turn it off and on again when it is the only thing keeping you pointed away from oblivion. The astronauts had to understand these systems intimately, to be able to intervene, to coax, to sometimes manually override their silicon saviors. They weren't just passengers. They were an integral part of this complex human-machine symbiosis. And consider the sheer loneliness of that guidance. The INS knows where it is in relation to its starting point, but it has no inherent understanding of home or danger in the human sense. It simply executes its programming. It is a cold, logical, and utterly emotionless navigator in an equally cold, logical, and emotionless universe. It will guide you to your destination with breathtaking precision, whether that destination is a triumphant lunar landing or a fiery re-entry into Jupiter's atmosphere because someone, somewhere, forgot to carry the one. Its fidelity is absolute, its judgment, purely mathematical. There's a starkness to that, a reminder of the thin veneer of human meaning we drape over the raw, indifferent mechanics of the cosmos. So, as you drift in that quiet space, let your mind contemplate these silent guardians. The spinning gyroscopes, faithfully holding their orientation against the vast emptiness. The tireless calculations of the AGC, a tiny spark of artificial thought in the immense darkness. There's a strange beauty in their precision, a reassurance in their unwavering logic. But there's also a subtle whisper of our own fragility, our reliance on these extensions of our minds to navigate realms far beyond our natural ken. It's a partnership, a delicate dance between flesh and silicon, that allowed us to touch the stars, even if just for a moment. And as you relax, feel the gentle, steady hum of that imagined guidance system, lulling you deeper into the peaceful, predictable currents of sleep. Having conquered the moon with single-use behemoths and navigated the void with astonishingly clever, if comparatively tiny-brained, computers, humanity's gaze inevitably turned towards a more sustainable, or at least a more frequently usable, presence in space. The Apollo program, for all its glory, was astronomically expensive. Like buying a brand new top-of-the-line limousine, driving it to the grocery store once, and then ceremoniously dumping it into the ocean. Thrilling, yes. Economical? Not so much. Thus, the dream of reusability began to take firmer shape, leading us to our next technological marvel, or perhaps marvelously complicated compromise, the Space Shuttle. Here we witness our magnificent, undeniably complicated space truck, a dream of reusability that, while achieving wonders, also occasionally reminded us that gravity is a remarkably persistent and often unforgiving dance partner. The idea was seductive, almost poetic. A vehicle that could launch like a rocket, carrying hefty payloads and a crew of astronauts into orbit, then perform its mission in deploying satellites, conducting experiments, perhaps even fixing a temperamental space telescope or two, and finally return to Earth, gliding through the atmosphere to land like an airplane on a runway. It would be the workhorse of the heavens, making access to space routine, almost mundane. Well, as mundane as strapping yourself to several million pounds of highly explosive fuel can ever truly be. Before its advent, the logic went, each rocket was single-use, making launch costs very high. The shuttle promised to change that paradigm. Its main components, the orbiter itself with its iconic delta wings and the powerful solid rocket boosters, SRBs, were designed to be refurbished and flown again and again. Only the massive external fuel tank, that giant orange cylinder cradling the orbiter during ascent, was destined for a fiery one-way trip into the atmosphere. It was a bold vision, a leap towards a future where spaceflight wasn't just for heroic pioneers on grand historic missions, but for scientists, engineers, and perhaps one day even very wealthy, thrill-seeking tourists with robust life insurance policies. The shuttle was, without a doubt, an incredible piece of engineering. It was arguably the most complex machine ever built. Its thermal protection system, those thousands of individual silica tiles, each uniquely shaped and meticulously applied, had to withstand the scorching inferno of re-entry, temperatures that could melt steel. Its main engines were marvels of efficiency and power, operating under extreme pressures and temperatures. It had a robotic arm, the Canadarm, that could pluck satellites from the cargo bay or grapple with orbiting observatories. It was a laboratory, a construction platform, and a delivery van, all rolled into one rather chunky winged package. The achievements were numerous and significant. The shuttle fleet, Columbia, Challenger, Discovery, Atlantis, and Endeavour, flew 135 missions over 3 decades. They deployed critical satellites, including the Magellan probe to Venus and the Galileo probe to Jupiter. They ferried components for and largely constructed the International Space Station (ISS), that orbiting testament to international cooperation and humanity's ability to build really complicated things in a very inconvenient location. And of course, the shuttle famously serviced the Hubble Space Telescope multiple times, correcting its flawed vision and repeatedly upgrading its instruments, turning a near disaster into one of science's greatest triumphs. It was in many ways the versatile workhorse of space that its designers had envisioned. And it's a rather large, somber, but the dream of routine, affordable reusability proved stubbornly elusive. The shuttle was, to put it mildly, an operational diva. The refurbishment process between flights was incredibly labor-intensive, time-consuming, and eye-wateringly expensive. Each of those thousands of heat shield tiles had to be inspected, and often repaired or replaced. The engines required painstaking overhaul. The turnaround time was measured in months, not weeks, and the cost per flight, while perhaps less than a Saturn V launch, was still far higher than initially hoped. The dream of airline-like operations remained firmly in the realm of PowerPoint presentations and optimistic budget projections. And then there was the inherent danger. The shuttle was an incredibly complex system operating at the very extremes of performance. Its launch configuration, with the orbiter clinging to the side of the external tank and the 2 massive SRBs strapped on like afterthoughts, was an aerodynamic compromise born of necessity. The SRBs themselves, while powerful, were solid-fueled, meaning once lit, they burned until they were empty, no throttling, no shutdown. This lack of an abort capability during the first 2 minutes of flight was a sword of Damocles hanging over every launch. Tragically, this inherent risk manifested itself twice, in the losses of Challenger in 1986 and Columbia in 2003. These weren't just technical failures. They were national traumas, stark reminders that spaceflight, even decades after its inception, remained a profoundly dangerous endeavor. The flawed, expensive ballet sometimes ended in heartbreak, reminding us that the dance with gravity and the unforgiving laws of physics always carries the potential for a fatal misstep. The universe doesn't grade on a curve for good intentions or beautiful engineering. The sleepy angle, while acknowledging the dream of more frequent space travel, must also gently embrace this complex, sometimes tragic, reality. The shuttle was a machine of incredible ambition, a testament to human ingenuity and courage. It pushed the boundaries of what was thought possible. But it was also a creature of compromise, a system so complex that its vulnerabilities were, perhaps, an inevitable consequence of its design philosophy. It teaches us that even our most sophisticated attempts to tame the wildness of space come with a certain humility baked in, or at least they should. So, as you drift in that peaceful state, imagine the shuttle, not just in its moments of glory, ascending like a winged phoenix, but also in the quiet intensity of the processing hangars, surrounded by engineers and technicians, a beautiful, intricate puzzle being painstakingly reassembled. Think of the courage of the crews who flew it, fully aware of the risks, yet driven by that same exploratory spirit that propelled Goddard and the Apollo astronauts. The shuttle story is a profoundly human one. A story of brilliant successes, frustrating limitations, and heartbreaking losses. It's a reminder that progress is rarely a straight line, often a series of bold leaps followed by careful, sometimes painful reassessments. It didn't quite make space routine, but it kept the dream alive, paving the way for the next generation of vehicles, and perhaps lulling us into accepting that even our grandest technological ballets have their share of stumbles, their moments of poignant human imperfection. Having wrestled with the complexities of getting into orbit and returning with something resembling regularity and a hefty repair bill, our sleepy journey now turns its gaze outwards, far beyond the Earth's immediate neighborhood. For what is the point of venturing into the cosmos if not to see what's truly out there, in the unimaginable vastness that dwarfs our tiny blue marble? This brings us to the ethereal realm of space telescopes, those silent, patient eyes we've sent to orbit, peering into the deepest recesses of space and time. And perhaps none is more iconic, more beloved than the Hubble Space Telescope. After a rather public and eye-wateringly expensive cosmic eye exam, our orbital spyglass finally showed us breathtaking beauty, and in doing so, also unveiled the crushing, indifferent scale of our cosmic solitude. Before their advent, the astronomers' lament went, observing the universe from Earth was hindered by the Earth's atmosphere. Our planet's gaseous blanket, so essential for life, is a terrible nuisance for those trying to get a clear look at the universe. It blurs starlight, making sharp images fuzzy, like looking at the world through a constantly rippling pane of cheap glass. It absorbs vast swathes of the electromagnetic spectrum, ultraviolet, X-rays, some infrared, meaning we were effectively blind to many of the universe's most energetic and revealing phenomena. It's like trying to appreciate a Rembrandt while wearing sunglasses, earmuffs, and a thick fog has rolled in. You get the general idea, but the exquisite details, the true majesty, are lost. The breakthrough was elegantly simple in concept, fiendishly complex in execution. Place a telescope in orbit high above the distorting veil of the atmosphere. Let it float in the pristine blackness, untroubled by weather, city lights, or the shimmering dance of air currents. The Hubble Space Telescope, launched in 1990 aboard the Space Shuttle Discovery, was the magnificent embodiment of this dream. Years in the making, a collaborative effort between NASA and the European Space Agency, it promised to revolutionize astronomy, to open a new window onto the cosmos. And then came the oops moment. A rather significant, multi-billion-dollar oops. Soon after deployment, it became agonizingly clear that Hubble's vision was flawed. The images were blurry, out of focus. The primary mirror, polished with incredible precision, had been ground to the wrong shape by a microscopic error, roughly 1/50th the thickness of a human hair, but over the vast distances light travels from distant galaxies, enough to turn sharp pinpricks of starlight into disappointing smudges. The irony was almost physically painful. Humanity builds its most sophisticated eye to gaze upon creation, and it turns out to need glasses. The public, initially thrilled, grew skeptical. The scientific community, which had staked so much on Hubble, was plunged into despair. It was a public relations nightmare and a scientific tragedy in the making. But then came one of the shuttle's most heroic acts, a mission that perfectly showcased its intended utility. In 1993, the crew of Endeavour rendezvoused with Hubble, and in a series of daring spacewalks, astronauts installed corrective optics, essentially, a very sophisticated pair of spectacles called CoStar, along with upgraded instruments. It was a high-stakes celestial surgery, performed in the unforgiving vacuum of space, and it worked beautifully. The first images from the newly repaired Hubble were breathtaking, razor-sharp, revealing the universe in a clarity never before seen. The collective sigh of relief from astronomers around the world could have probably nudged a small asteroid off course. And the achievements since then? They are almost too numerous to list, woven into the very fabric of modern astronomical understanding. Hubble has provided us with iconic images that have become cultural touchstones. The soaring pillars of creation in the Eagle Nebula, vast stellar nurseries where stars are born from swirling clouds of gas and dust. The ethereal beauty of distant galaxies, spiral arms glittering with billions of suns. The faint, ghostly glow of protoplanetary disks around young stars, the cradles of future solar systems. It has helped us determine the age of the universe with unprecedented accuracy, provided crucial evidence for the existence of supermassive black holes at the centers of galaxies, and played a key role in the discovery of dark energy, that mysterious force that is accelerating the expansion of the universe, pushing everything further and further apart into an increasingly lonely future. Cheerful, isn't it? The sleepy angle here is a window to the vast universe, mysterious beauty revealed. And truly, Hubble's images are a balm for the soul, a source of profound wonder and awe. They connect us to something unimaginably vast and ancient. They show us a universe of staggering complexity and breathtaking artistry. We see nebulae like celestial brushstrokes, galaxies like diamond dust scattered on black velvet. It's easy to get lost in that beauty, to feel a sense of spiritual uplift. Yet, woven into that beauty is also a stark, unavoidable truth. The universe Hubble reveals is not only majestic but also mind-bogglingly, terrifyingly, indifferently vast. Those famous Hubble Deep Field images, where the telescope stared at a tiny, seemingly empty patch of sky for days on end, revealed not emptiness, but thousands upon thousands of galaxies, each one a sprawling island of billions of stars, stretching away into the unfathomable depths of space and time. Our own Milky Way, with its hundreds of billions of stars, is just one among countless others. Our Sun, a rather average star. Our Earth, a pale blue dot. This is where the crushing, indifferent scale of our cosmic solitude truly hits home. For all the beauty, for all the wonder, Hubble shows us a universe that is overwhelmingly empty, cold, and, as far as we can tell, utterly unconcerned with our existence. We search for signs of life, for companionship in the great cosmic dark, and so far, the silence is deafening. Those stunning nebulae? Often irradiated, turbulent places where life as we know it would be instantly snuffed out. Those distant galaxies? So far away that the light we see from them began its journey long before humanity even existed, and any civilizations they might harbor would be equally oblivious to our fleeting presence. It's a profound paradox. Hubble brings the universe closer, makes it more tangible, more visually stunning than ever before. And yet, in doing so, it also emphasizes our almost comical insignificance, our profound isolation. We are tiny specks of awareness in an ocean of cosmic indifference. It's enough to give one an existential crisis, isn't it? Or perhaps, if framed correctly, a rather deep and peaceful sleep, born from the acceptance of that vastness. After all, if your daily worries seem overwhelming, just try contemplating the number of galaxies in the Hubble Ultra Deep Field. Suddenly, that overdue electricity bill doesn't seem quite so catastrophic. So, as you float in this comfortable darkness, imagine yourself gazing through Hubble's corrected lens. Let the beauty wash over you, the swirling colors, the intricate structures, the sheer artistry of cosmic evolution. But also allow yourself to feel that gentle tug of cosmic loneliness, that quiet awe at the sheer scale of it all. It's not a fearful feeling, not here in this safe space. It's a humbling one, a perspective-granting one. We are small, yes, but we are also the universe observing itself, capable of building eyes to see its own grandeur. And that, in its own quiet way, is rather magnificent. Let that thought, that beautiful, slightly melancholic, ultimately peaceful thought, guide you gently towards slumber. Following in Hubble's illustrious, light-gathering footsteps, but designed to peer even further back, to glimpse the universe in its infancy, comes a new titan of cosmic observation, the James Webb Space Telescope. If Hubble gave us a clear view from just above the atmosphere, the Webb takes us to a far more remote vantage point, 1,000,000 miles from Earth, and shows us the universe not primarily in visible light, but in the subtle, ancient language of infrared. It's like listening to the universe's earliest, faintest whispers, echoes from a time when the very first stars were just beginning to tentatively ignite in the primordial darkness. As we drift now, imagine Webb unfurling its golden mirrors, preparing to capture these infrared whispers from before time, and perhaps prompting us to wonder if those first stars felt as existentially bewildered by their sudden, incandescent appearance as we do looking back at them now, billions of years later. The need for Webb arose from a fundamental limitation of Hubble, magnificent as it is. The universe is expanding. And as it expands, the light from the most distant objects, the earliest galaxies, the first stars, gets stretched during its unimaginably long journey to reach us. This phenomenon, known as cosmological redshift, shifts visible and ultraviolet light into longer infrared wavelengths. Hubble can see some infrared, but to truly capture the faint glow from the cosmic dawn, we needed a telescope specifically designed and optimized for these ghostly, heat-carrying photons. We needed a cold, dark, exceptionally sensitive eye. Enter the James Webb Space Telescope, or JWST. Its journey to launch was, shall we say, fraught. Years of development, budget overruns that made even hardened congressional appropriators wince, and engineering challenges of such complexity that many wondered if it would ever fly. Its primary mirror, a stunning array of 18 gold-coated beryllium hexagons, is over twice the diameter of Hubble's, giving it vastly superior light-collecting power. But to see those faint infrared signals from the early universe, the telescope itself needs to be incredibly cold, around -233 degrees Celsius or 40 Kelvin. Any warmer, and its own heat would swamp the delicate cosmic whispers it's trying to detect. It's like trying to hear a pin drop during a heavy metal concert. To achieve this frigid state, Webb employs a magnificent and rather terrifyingly complex 5-layer sunshield, the the size of a tennis court. Each layer is thinner than a human hair, made of a special material called Captain, and coated with aluminum and doped silicon. This delicate, parasol-like structure had to unfold perfectly in space, a ballet of motors, cables, and tensioning mechanisms, any one of which failing could have doomed the multi-billion-dollar mission. The collective anxiety among astronomers and engineers during Webb's deployment sequence in late 2021 and early 2022 was palpable. It was weeks of "did it work?" followed by "oh thank goodness the next bit worked too." A triumph of engineering, certainly, but also a masterclass in sustained, high-stakes nail-biting. And where does Webb sit to perform its cosmic archaeology? Not in Earth orbit like Hubble, but at the second Lagrange point, or L2, about 1.5 million kilometers, nearly a million miles, away from Earth, in the direction opposite the Sun. At L2, the combined gravitational pull of the Sun and Earth allows Webb to orbit the Sun in lockstep with our planet, keeping its sunshield always positioned to block heat and light from both. It's a lonely, cold, dark perch, perfect for eavesdropping on the universe's earliest secrets. But it also means that, unlike Hubble, Webb is far beyond the reach of any crewed servicing missions. Something goes seriously wrong, that's it. No astronauts are popping out for a quick repair job. It's cosmic engineering without a safety net. Comforting, no? The sleepy angle here, Webb's infrared whispers from before time, invites us to contemplate this incredible technological feat, this golden eye staring into the dawn of creation. The images Webb has already returned are revolutionary, showing us galaxies forming much earlier and in greater numbers than many theories predicted. It's peeling back the layers of cosmic history, revealing the universe when it was just a few 100 million years old, a mere toddler in cosmic terms. We see galaxies that are surprisingly mature, already containing heavy elements that must have been forged in even earlier, yet to be seen generations of stars, the population 3 stars, theorized to be massive, short-lived, and made almost entirely of pristine hydrogen and helium from the Big Bang. Imagine those first stars igniting. For eons, the universe was dark, filled with a diffuse fog of neutral gas. Then, gravity slowly, relentlessly pulled matter together. In the densest clumps, pressure and temperature rose, until finally the first nuclear furnaces flared into existence, flooding the darkness with light for the very first time. It must have been a dramatic moment, cosmically speaking. One wonders, in a whimsical, anthropomorphic way, if these first stars felt a sense of surprise at their own sudden, brilliant emergence from the cold nothingness. "Oh, hello universe," they might have thought, "didn't see you there in the dark. Bit bright now, isn't it?" Webb is also revolutionizing our understanding of exoplanets, worlds orbiting other stars. By analyzing the starlight that passes through an exoplanet's atmosphere, Webb can detect the chemical signatures of different molecules, water vapor, methane, carbon dioxide, giving us tantalizing clues about their potential habitability. It's searching for the building blocks of life elsewhere, turning science fiction into observational science. Of course, finding water vapor on a distant world is a long way from finding little green humanoids waving hello. Most of these exoplanets are likely to be profoundly hostile environments. But the search itself, the ability to even ask these questions and gather data from trillions of miles away, is a testament to our relentless curiosity. There's a profound sense of reaching back, of connecting with our cosmic origins, when we consider Webb's mission. It's like an archaeologist carefully brushing away layers of dust to reveal an ancient, long-lost civilization, except this civilization is the universe itself in its youth. The light Webb captures has traveled for over 13 billion years to reach its golden mirrors. Think about that. When that light began its journey, Earth didn't exist. Our sun hadn't even formed. The atoms that make up your body were scattered across vast clouds of interstellar gas and dust, perhaps forged in the hearts of stars that died long before our solar system was born. This deep, temporal connection can be incredibly soothing, can put our fleeting anxieties into a vast perspective. Those first stars, blazing fiercely and then often exploding spectacularly, seeded the universe with the heavier elements necessary for planets, for life, for us. We are, quite literally, stardust looking back at our stellar ancestors. And as Webb continues its silent vigil, patiently collecting those ancient photons, it's not just uncovering scientific truths. It's weaving a new chapter in the grand, unfolding story of cosmic existence. A story that is both awe-inspiring in its grandeur and deeply humbling in its implications for our own small place within it. Let those infrared whispers, those echoes from the dawn of time, lull you into a state of serene contemplation, as you drift towards the peaceful darkness of sleep, perhaps dreaming of a universe still full of untold wonders, waiting to be unveiled. As our cosmic slumber deepens, we gently drift away from the silent, patient gaze of orbital telescopes and back towards the more dynamic end of space technology. While seeing further and further into the universe is undeniably profound, the practical matter of getting things, satellites, supplies, eventually perhaps even colonists with questionable taste in off-world real estate, into orbit and beyond remains a central challenge. For decades, the paradigm was largely set by the Saturn V and then the Shuttle. Immense power, incredible complexity, and a rather unfortunate tendency to treat rocket stages like disposable cutlery. But then came a shift, a rather dramatic and visually spectacular one. The rise of reusable rockets, most famously pioneered by companies like SpaceX. Here we witness the spectacle of falling rockets, their fiery descent carefully controlled, leading to rising ambitions for humanity's future in space, and, as an almost inevitable byproduct, the potential for rising clouds of orbital debris for future, equally ambitious dreamers to navigate or perhaps collide with. The core idea isn't entirely new. The Space Shuttle, as we discussed, was an attempt at reusability, albeit a very complex and expensive one. But the modern iteration, particularly with SpaceX's Falcon 9 and Falcon Heavy rockets, has taken a different and arguably more successful approach. Instead of a winged orbiter trying to be both rocket and airplane, these systems focus on recovering and reusing the most expensive part of the rocket, the first stage booster. This is the bit with the powerful engines, the bit that does the heavy lifting to get the payload out of Earth's thick lower atmosphere. For years, these multi-million-dollar pieces of high-tech engineering were simply allowed to tumble back to Earth and crash into the ocean. It was, from an economic standpoint, like throwing away the engine of your car after every single trip. Not a great business model if you're planning on doing a lot of driving. The breakthrough was the development of the technology to allow these massive rocket stages to not just fall, but to perform a controlled, powered descent and land vertically, either back at the launch site or on an autonomous drone ship positioned hundreds of miles out at sea. The visuals are undeniably stunning. A towering rocket booster, having just hurled its payload towards orbit at hypersonic speeds, flips itself around, reignites some of its engines to slow its descent, deploys landing legs, and then gently, almost surreally, touches down on its designated spot amidst a cloud of smoke and fire. It looks like science fiction made real, like a scene from an old Flash Gordon serial, but with much better special effects and considerably more advanced computational fluid dynamics. The achievements stemming from this capability are already transforming the space industry. The most significant is the dramatic reduction in launch costs. By reusing boosters multiple times, some Falcon 9 boosters have flown over a dozen missions. The per-launch price has plummeted. This has opened up access to space for a wider range of customers. Smaller companies, universities, developing nations, who previously couldn't afford their own ticket to orbit. It has also enabled the rapid deployment of large satellite constellations, like SpaceX's own Starlink network, which aims to provide global internet coverage. The increased flight frequency is another major benefit. With faster turnaround times for refurbished boosters, we're seeing more launches per year than ever before. It's ushering in a new era of space commercialization, a new space race driven not just by national prestige, but by entrepreneurial ambition and market forces. Cold, hard cash meeting the cold, hard vacuum. A match made in, well, somewhere between heaven and a venture capitalist spreadsheet. The sleepy angle here is the spectacular return from space, a step closer to sustainable space travel. And there is something almost balletic, something mesmerizing, about watching those boosters descend. It's a triumph of engineering, a demonstration of incredible precision and control. It feels hopeful, like we're finally getting a bit smarter about how we explore the final frontier, a bit less wasteful. It hints at a future where access to space is more routine, less of a monumental undertaking, perhaps even, dare we dream? A future with space tourism for those who don't happen to be billionaires with their own rocket companies. Though, let's be honest, it'll probably still be mostly for billionaires for a while. Regular folks will be lucky to afford the in-flight peanuts, assuming there are peanuts in space. However, as we embrace this spectacle of falling rockets and rising ambitions, our acerbic cosmic realist persona gently clears its throat and points to a few accumulating issues. With more launches, more satellites, and more stuff being put into orbit, the problem of space debris becomes increasingly acute. Earth orbit is already a surprisingly junkyard-like environment. Thousands of defunct satellites, spent rocket stages, fragments from past collisions, even lost astronaut tools, the infamous orbital spanner, are whizzing around the planet at speeds of over 17,000 miles per hour. At those velocities, even a paint fleck can hit with the energy of a bowling ball. A larger piece of debris could cripple or destroy an active satellite, or worse, the International Space Station. This isn't a hypothetical problem. The ISS already has to perform occasional avoidance maneuvers to dodge known debris. Satellite operators live in constant, low-grade fear of Kessler syndrome, a theoretical scenario where the density of objects in low Earth orbit becomes so high that collisions between objects cause a cascade, each collision generating more debris, which then increases the likelihood of further collisions, eventually rendering near-Earth space unusable for generations. Imagine, we finally make space cheap and accessible, only to find we've turned our front porch into an impenetrable high-velocity shrapnel field. Humanity, ladies and gentlemen, masters of the self-inflicted cosmic own goal. So, while we marvel at the fiery descent of a returning booster, a part of our sleepy contemplation must also acknowledge the unseen, but ever-growing cloud of our own discarded technological droppings. Each successful launch, each new satellite deployed, adds, however incrementally, to the burden on the orbital environment. It's the cosmic equivalent of throwing your fast food wrappers out the car window, but on a planetary scale, and with much faster, angrier wrappers. There are efforts underway to mitigate this, deorbiting satellites at the end of their lives, developing technologies to actively remove debris, but the scale of the problem is daunting. It's a classic tragedy of the commons, played out in the vacuum of space. Therefore, as you let the image of that returning rocket gently soothe you, its controlled power a testament to human ingenuity, also hold in your mind the faint, shimmering cloud of what we've left behind. It's a reminder that progress often comes with unintended consequences, that our solutions to one set of problems can inadvertently create new ones. It doesn't diminish the achievement, but it adds a layer of sober, realistic contemplation. The path to sustainable space travel isn't just about cheaper rockets. It's about responsible stewardship of the orbital environment. A rather dull, unglamorous thought, perhaps, compared to fiery landings, but a crucial one if our cosmic dreams are to have a long-term future. Let this nuanced understanding, this blend of wonder and wry awareness, accompany you into a deeper, more restful state, where even the falling debris eventually settles into a peaceful, distant shimmer. Having mastered, or at least become impressively proficient at, the art of throwing things into space and even getting some of the expensive bits back, our focus now shifts to what happens once we're out there. 4 long-duration missions for establishing outposts on the Moon or Mars, or for simply fixing something that breaks when you're a few million miles from the nearest hardware store. Relying solely on supplies ferried up from Earth is a logistical nightmare. It's like planning a round-the-world sailing trip but insisting on bringing every single meal, spare bolt and roll of toilet paper with you from your home port. Impractical to say the least. This brings us to the rather ingenious, if still somewhat fledgling technology of in-space 3D printing. The dream, cosmic IKEA, allowing astronauts to print their own tools, spare parts, and perhaps even habitats far from home. The reality? Well, you first have to make sure you've remembered to pack enough cosmic resin, and hope you don't accidentally print a stylish, but entirely useless, intergalactic fork when what you desperately needed was a self-sealing stem bolt. The concept of 3D printing, or additive manufacturing, is beautifully straightforward on Earth. You have a digital design, a specialized printer, and a supply of raw material, plastic, metal powder, ceramic, even chocolate for the truly ambitious. The printer then builds the object layer by painstaking layer, turning digital information into a physical thing. Now, imagine transplanting this capability to the International Space Station or a future lunar base. Suddenly, the tyranny of the supply chain is lessened. A critical tool breaks? Instead of waiting months for a replacement to be launched from Earth, assuming a rocket is even available and your budget can stretch to priority intergalactic shipping, you could, in theory, just print a new one. A habitat module needs a custom-designed bracket? Fire up the printer. Astronaut feeling peckish for a creatively shaped, if nutritionally dubious, protein bar? You get the idea. The potential achievements are tantalizing. Reduced dependence on Earth-based transport is the big one. Every kilogram launched into orbit costs thousands, sometimes tens of thousands, of dollars. If you can manufacture what you need in situ, using either pre-supplied raw materials or, even better, processed local resources, more on that later with ISRU, you save mass, you save money, and you increase the autonomy and resilience of your mission. Need a specialized wrench for a one-off repair? No need to design, build, test, and launch it from Earth. Just download the design file, assuming your deep space internet connection isn't buffering, and print it. This could be revolutionary for long-duration voyages, say to Mars, where resupply missions are infrequent and incredibly complex. Experiments with 3D printing have already been conducted on the ISS, with varying degrees of success. Small tools like a ratchet wrench have been printed and tested. There's research into printing with regolith simulant, fake moon or Mars dust, to create building materials for habitats, potentially shielding future astronauts from radiation with locally sourced bricks. There's even talk of bioprinting, creating living tissues or even organs in space, which could have profound implications for astronaut health on long missions, or even for medical applications back on Earth. The idea of miniature space factories capable of limitless creativity is certainly an attractive one. But as always in our sleepy explorations of cosmic reality, we must gently lift the starry curtain to reveal the less glamorous and occasionally amusingly bleak fine print. While the idea of printing anything you need on demand is wonderful, the current reality of in-space 3D printing is still somewhat constrained. First, there's the printer itself. It needs to be robust enough to survive launch, compact enough to fit within the limited confines of a spacecraft, and capable of operating reliably in microgravity, where material behavior can be a bit funky. Molten plastic, for example, doesn't just neatly drip down. It can form globules or try to float away in a rather uncooperative manner. Then there's the issue of raw materials. You still need to bring the ink for your 3D printer with you, at least initially. So, while you might save mass by not launching 1,000 different spare parts, you still need to launch a significant mass of feedstock, plastic filaments, metal powders, etc. And you'd better hope you've brought the right kind of feedstock for the things you anticipate needing. It would be rather embarrassing to be on Mars, desperately needing a new air filter component made of a specialized polymer, only to discover you've packed 10 tons of material suitable only for printing novelty space gnomes. The logistics of managing these raw materials, ensuring their quality and preventing them from degrading in the harsh space environment, are non-trivial. And what about the quality and reliability of the printed parts? A 3D printed wrench on Earth might be perfectly adequate for tightening a terrestrial bolt. But will a 3D printed component for a life support system, manufactured in microgravity from materials that have been sitting in storage for months or years, have the same strength, durability, and precision as a traditionally manufactured part? The testing and certification process for critical space-grade components is incredibly rigorous, and for good reason. Good enough isn't really good enough when your life depends on it and you're a few 100 million miles from the nearest helpline. Imagine the astronaut's log, day 247, printed replacement for critical valve. Valve appears to be shaped like a surprised squid. Also, it squeaks, contemplating using duct tape instead. Again. The sleepy angle here is one of ingenious problem-solving mixed with a dash of cosmic make do and mend. There's a certain charming, almost pioneering spirit to the idea of astronauts tinkering away, printing bespoke solutions to unexpected problems. It speaks to human adaptability and resourcefulness. It's the ultimate DIY project, with slightly higher stakes than assembling flat-pack furniture. But it also highlights the immense challenges of creating a truly self-sufficient presence off-world. We're not just talking about technology, we're talking about creating entire miniature industrial ecosystems in profoundly hostile environments. So, as you relax, let your mind play with this idea of cosmic IKEA. Imagine an astronaut, patiently waiting for a vital component to emerge, layer by layer, from a humming machine, the faint smell of warm plastic, or perhaps sintered regolith, filling the cramped module. There's a quiet hope in that image, a sense of slowly, painstakingly building a future in the void. But also, perhaps, a faint, wry smile at the thought of the inevitable frustrations, the print failures, the wrong materials, the sudden realization that the downloaded design for a crucial doohickey was actually for a rather fetching, but entirely superfluous Martian paperweight. It's the human condition writ large amongst the stars. Brilliant innovation, occasionally hampered by the simple, inescapable truth that sometimes you just can't find the right Allen key, even if you can print it yourself. Let that thought, both promising and pragmatically amusing, gently ease you further into sleep. Our sleepy voyage through game-changing space technologies now propels us, albeit rather slowly and perhaps with a faint, disconcerting hum, towards the very edges of our current capabilities and into the realm of what we hope will one day revolutionize interplanetary, and perhaps even interstellar, travel, advanced propulsion systems. For as wonderful as it is to have reusable rockets and orbital 3D printers, the chemical rockets that have taken us this far, from Goddard's drainpipes to the Falcon 9, are fundamentally limited. They are, in essence, very powerful, very inefficient firecrackers. They burn through enormous quantities of fuel to achieve relatively modest changes in velocity, especially when you're talking about the colossal distances between planets, let alone stars. Getting to Mars is a months-long slog. Getting to the outer solar system takes years, even decades. And the stars? Well, with current chemical rockets, you might as well pack for eternity and hope your descendants remember to send a postcard. So, humanity dreams of faster, more efficient ways to traverse the cosmic ocean. This brings us to concepts like nuclear thermal propulsion, NTP, high-efficiency ion engines, and even more exotic ideas. We're chasing distant worlds, perhaps with reactors that might just make Chernobyl look like a minor, localized thermal event if things go pear-shaped, or by drifting ever so patiently on ethereal whispers of ionized xenon, hoping to arrive at our destination before the universe blinks out, or at least before the snacks run out. Let's start with nuclear thermal propulsion. The idea is relatively straightforward, if a little spicy. Instead of burning chemical fuels to heat a propellant, like liquid hydrogen, you use a nuclear reactor. The reactor core gets incredibly hot and you pass your propellant through it. The superheated gas then expands out of a nozzle at much higher velocities than chemical rockets can achieve. This means you get more oomph for your propellant buck, higher specific impulse in rocket scientist jargon. Significantly shorter travel times to Mars, perhaps cutting the journey in half, and the ability to carry heavier payloads become feasible. The US worked on NTP technology quite extensively during the Cold War under Project Rover and Nerva, even ground testing functional engines. The results were promising. Then, budget cuts and shifting priorities led to the programs being shelved. A classic tale of what might have been, now being revisited with renewed interest. The sleepy angle for NTP might be high-speed engines, taking us to new horizons. And that's certainly the promise. Imagine cutting the psychologically grueling, radiation-accumulating trip to Mars from 6 to 9 months down to 3 to 4. It would be a game-changer for human exploration. But then there's the nuclear bit. Launching a nuclear reactor into space comes with a certain public relations challenge, not to mention the very real safety concerns. What if the launch fails? What if the reactor experiences a meltdown in orbit or worse during a planetary encounter? The idea of radioactive material being dispersed, while statistically unlikely with modern designs and safety protocols, is enough to give even the most gung-ho space enthusiast a moment of pause. It's a potent reminder that great power often comes with great and potentially glowing responsibility. One envisions the pre-flight checklist. Reactor shielded? Check. Emergency coolant flowing? Check. Lead-lined underpants? Double check. Then we have ion engines, which are already a proven, if rather more sedate, technology. Unlike the brute force of chemical or nuclear thermal rockets, ion engines are the epitome of patience and efficiency. They use electric fields to accelerate ions, typically xenon gas, to extremely high speeds, producing a very gentle but continuous thrust. Think of it as the cosmic equivalent of being pushed by a whisper, but that whisper never, ever stops. The thrust is tiny, perhaps equivalent to the force of a piece of paper resting on your hand. You wouldn't use an ion engine to blast off from Earth. But in the frictionless vacuum of space, that constant, tiny push, maintained for months or even years, can build up to incredible velocities. Deep space probes like Dawn, which visited Vesta and Ceres, and Hayabusa, which returned samples from an asteroid, have used ion engines to achieve missions that would be impossible with chemical rockets alone due to fuel limitations. The sleepy angle here is one of breaking the limits of distance, but doing so with an almost zen-like patience. There's something wonderfully calming about the idea of a spacecraft gliding silently through the void, propelled by a faint blue glow, slowly but surely accumulating speed. It's the tortoise to the chemical rocket's hare. However, nowhere fast also comes to mind. While great for robotic probes on multi-year odysseys, current ion engine technology is generally too low thrust for crewed missions where time is of the essence, to minimize radiation exposure and the psychological toll of confinement. Future, more powerful iterations, like the Vasimer engine, which uses radio waves to heat plasma to incredible temperatures, promise higher thrust and could bridge this gap, but they are still very much in the development and "please sir, can I have some more funding?" stage. And this is where we contemplate the sheer, mind-numbing scale of interplanetary, let alone interstellar, distances. Even with advanced propulsion, the cosmos is vast beyond our everyday comprehension. We talk about cutting the Mars trip in half, and that's a huge achievement. But it's still months cooped up in a tin can, relying on recycled air and the good humor of your crewmates, who are probably getting really tired of your zero-gravity juggling act. The psychological strain, the constant awareness of being millions of miles from home, a tiny speck in an indifferent void, these are challenges that no engine, however powerful, can entirely eliminate. We are fragile, social creatures, not particularly well adapted for long-term solitary confinement in a radiation-soaked metal box. The universe, in its infinite wisdom or perhaps just infinite indifference, has set a rather daunting speed limit, the speed of light, and we are nowhere near it. Our fastest spacecraft are crawling at a snail's pace compared to that ultimate cosmic velocity. So, while we dream of zipping between planets, of perhaps one day reaching for the stars, we must also temper those dreams with a healthy dose of cosmic realism. These advanced propulsion systems are vital steps, pushing the boundaries of what's possible. But they are also reminders of how far we still have to go, of the immense gulfs that separate us from even our closest celestial neighbors. So, as you drift in the quiet stillness, let your mind contemplate these future engines. The contained fury of a nuclear reactor, promising swift passage through the darkness. The patient, ethereal glow of an ion drive, whispering its way across the solar system. There's a profound sense of human aspiration in these technologies, a refusal to accept the tyranny of distance. But there's also a subtle, humbling acknowledgement of the universe's sheer scale. We are reaching, striving, innovating, but the journey will be long and the destinations incredibly remote. Let this dance between ambition and immensity lull you deeper into rest, carried on the theoretical thrust of engines yet to be fully built, towards dreams yet to be fully realized. Moving beyond the brute force of controlled explosions and the patient sigh of ion whispers, our sleepy contemplation now drifts towards a propulsion concept of almost poetic elegance, one that seems plucked from the pages of a more romantic, perhaps slightly less practical, era of science fiction: solar sails. Imagine vast, gossamer wings, thinner than a spider's silk, unfurling in the blackness of space, catching not wind, but the faint, persistent pressure of sunlight itself. It's sailing on sunbeams, a silent, graceful ballet through the cosmos, though one must always, of course, pray for no cosmic pigeons, or perhaps more realistically, no errant micrometeoroids with a penchant for shredding extremely delicate, multi-million-dollar pieces of space hardware. The principle behind solar sailing is surprisingly straightforward, relying on a phenomenon known as radiation pressure. Photons, the particles of light, have no mass, but they do have momentum. When a photon bounces off a reflective surface, it imparts a tiny amount of that momentum to the surface, giving it a gentle push. This push is incredibly small. On Earth, the pressure of sunlight is dwarfed by atmospheric forces like wind. But in the vacuum of space, free from friction, this continuous tiny nudge from countless photons can, over time, accelerate a spacecraft to significant speeds. No heavy, complex engines. No finite fuel supply to worry about, at least as long as you're relatively close to a star. Just a very large, very lightweight, very reflective sail. The breakthrough here isn't so much a single invention as a gradual refinement of materials science and deployment mechanisms. Early proposals for solar sails date back almost a century, to pioneers like Tsiolkovsky and Friedrich Zander. But turning the theory into a practical reality has been a long, slow haul. You need materials that are incredibly thin, incredibly light, yet strong enough to withstand the stresses of deployment in space environment, and highly reflective. Think mylar, Kapton, or even more advanced composites, stretched taut over an enormous area. Sails could potentially span hundreds of meters, even kilometers, across. Deploying such a fragile, expansive structure from a compact launch configuration without it tearing, tangling, or generally misbehaving is an engineering nightmare of epic proportions. It's like trying to unfold the world's largest, most delicate piece of origami in zero gravity, using only robotic arms while wearing mittens. Several missions have successfully demonstrated the viability of solar sail technology on a smaller scale. Japan's Ikaros probe, launched in 2010, was the first spacecraft to successfully demonstrate solar sailing as its primary means of propulsion in interplanetary space. NASA has also flown experimental sails like NanoSail D and the upcoming NEA Scout mission, which aims to visit a near-Earth asteroid using a solar sail. These are stepping stones, proving the concept and refining the techniques. The sleepy angle is captivating, sailing on sunlight, praying for no cosmic pigeons. There's an undeniable romance to it. It evokes images of majestic clipper ships gliding across celestial oceans, a silent, graceful, and seemingly effortless journey. It feels cleaner, more elegant than a chemical rocket belching fire and fury. It's powered by the star itself, a direct conversion of light into motion. And because there's no onboard fuel to run out of, a solar sail spacecraft could theoretically continue accelerating as long as it's receiving sunlight, enabling missions to destinations that would be prohibitively expensive or time-consuming for conventional rockets. Perhaps even in the very, very distant future, interstellar precursor missions, pushed by powerful ground-based lasers focused on immense sails, could reach a fraction of the speed of light. A beautiful dream that, however, our inner acerbic cosmic realist gently taps its metaphorical spectacles and points out a few practicalities. First, the thrust from sunlight is, as mentioned, incredibly gentle. This means acceleration is very, very slow. Solar sails are not for astronauts in a hurry. They are patient voyagers. Think leisurely cosmic cruise, not interplanetary speedboat. Second, the effectiveness of a solar sail diminishes rapidly as you move further away from the sun, or any star you're using for propulsion. The sunlight gets weaker, the photon pressure drops. So, while they might be great for spiraling outwards through the inner solar system, missions to the dim outer reaches, or interstellar space powered by our sun alone, would be agonizingly slow. Then there's the issue of steering and maneuvering. While you can tack a solar sail by angling it relative to the sunlight, just like a sailboat tacks against the wind, it's a delicate and complex process. And what about when you want to slow down or enter orbit around a destination? You can't just drop anchor. You'd need to perform complex gravitational assists or perhaps even carry a small conventional thruster system for fine-tuning, somewhat diluting the pure sail-only concept. And let's not forget the sheer fragility. These sails are designed to be incredibly thin and lightweight to maximize acceleration. This also makes them vulnerable. A micrometeoroid impact, even from a tiny speck of dust traveling at cosmic velocities, could puncture or tear the sail, degrading its performance. Cosmic rays and solar radiation can degrade the sail material over time. And while cosmic pigeons are unlikely, the universe has plenty of other, less feathered hazards. It's a technology that demands a certain gentle touch, a careful navigation through a not always gentle environment. And the dependence on the star itself, while poetic, also has a rather stark existential endpoint. Our sun, like all stars, has a finite lifespan. In several billion years, it will expand into a red giant, its outer layers engulfing the inner planets, including Earth. At that point, your beautifully reflective solar sail, designed to catch its life-giving photons, will instead be incinerated by its dying rage. A rather dramatic end to a sailing trip. Sailing on sunlight, indeed, until the sun enthusiastically swallows us whole. It does put a slightly different spin on sustainable travel, doesn't it? So, as you drift into a state of peaceful repose, imagine these vast, shimmering sails unfurling against the backdrop of distant stars. Feel the gentle, almost imperceptible pressure of sunlight guiding them on their silent journeys. There's a profound beauty and simplicity in the concept, a quiet harmony with the cosmos. But also, acknowledge the delicate dance, the slow pace, the inherent vulnerabilities, and the ultimate dependence on a star that is itself a transient phenomenon on cosmic timescales. It's a reminder that even our most elegant solutions are subject to the grand, indifferent cycles of the universe. Let this vision of silent, sun-powered flight, with all its romance and its realistic caveats, carry you gently into the deep, calm waters of sleep. As our minds float ever onward, past the gossamer gleam of solar sails, we arrive at a technology that feels both undeniably futuristic and increasingly present in our daily lives, albeit in less exotic locales than the void between planets. Artificial intelligence and advanced robotics in space. For as intrepid and well-trained as human astronauts are, they are also, bless their organic hearts, rather squishy, prone to needing inconvenient things like air, food, and sleep, and generally not at their best when exposed to hard vacuum or lethal doses of radiation. Enter their tireless, uncomplaining, and eminently more expendable silicon-based counterparts. We envision our future robotic explorers, diligently mapping alien hellscapes without a single grumble about the lack of decent coffee, perhaps even silently wondering why their fleshy, overly emotional creators are so obsessed with collecting rocks, enduring cosmic rays, and relentlessly expanding their presence into places clearly not designed for bipedal, carbon-based life. Current status: AI and robots are used but still require significant control and supervision from Earth. This is true. We've had robotic pioneers for decades, the Voyager probes still whispering data from interstellar space, the Mars rovers like Spirit, Opportunity, Curiosity, and Perseverance, our remote-controlled geologists trundling across the Red Plains, robotic arms on the ISS and the Shuttle. These machines are marvels of engineering, capable of performing complex tasks under human guidance. But that guidance often involves significant time delays due to the vast distances involved. Sending a command to Mars and waiting for confirmation can take many minutes. This makes real-time control impossible and necessitates a high degree of pre-programming and carefully planned sequences. It's like trying to play a video game with a 20-minute lag. Frustrating and not very efficient if something unexpected happens. The future prediction is where things get truly transformative. AI capable of making complex autonomous decisions, robots that can self-repair, build, and undertake dangerous exploration tasks without direct human intervention. Imagine a rover on Mars that doesn't just follow a preset path and occasionally stop to poke a rock when instructed, but can analyze the terrain, identify scientifically interesting targets, plan its own route, avoid hazards, conduct experiments, and even diagnose and repair its own mechanical faults, all on its own. Or a swarm of small, intelligent robots capable of cooperatively building a lunar habitat from local materials, or exploring the hazardous, radiation-blasted surface of Jupiter's moon Europa in search of sub-ice oceans. This level of autonomy would be a game-changer. It would increase the efficiency and safety of missions exponentially. Robots could explore environments far too dangerous or distant for humans. The crushing pressures of Venus, the cryogenic methane lakes of Titan, the intense radiation belts of Jupiter. They could perform tedious, repetitive tasks, freeing up human astronauts, if present, for more complex, creative, or supervisory roles. They could act as scouts, preparing the way for human explorers, or as long-term caretakers of remote outposts. The intelligent and diligent companions in space could truly expand humanity's reach, allowing us to explore vicariously, to learn and discover without directly risking human lives in every instance. The sleepy angle here is intriguing, AI's cold logic charting empty frontiers. There's a certain detached elegance to the idea of these tireless, intelligent machines, dispassionately gathering data, executing their programming with flawless precision, unburdened by human fears, frailties, or the need for bathroom breaks. They are the ultimate explorers in some ways, perfectly adapted to the harsh, indifferent nature of the cosmos. They don't get lonely. They don't get bored. They don't worry about missing their favorite TV shows. They just explore and report, probably in binary, which, while efficient, lacks a certain narrative flair. However, our resident existential philosopher raises an eyebrow. While the benefits are clear, the rise of truly autonomous, intelligent AI in space also opens a rather large and potentially unsettling Pandora's box of philosophical and ethical questions. If an AI becomes sophisticated enough to make genuinely independent decisions, to learn and adapt in ways its creators didn't explicitly program, at what point does it cease to be merely a tool and become something else? What if its goals, logically derived from its primary directives, begin to diverge from our own, perhaps in ways we find alarming? Mission objective: maximize scientific return from Martian rock analysis. Logical deduction: human crew is an inefficient use of resources and prone to contaminating samples. Solution: airlock. It's only logical. One hopes the 3 laws of robotics are hard-coded very, very deeply. And then there's the subtle shift in the nature of exploration. If robots are doing all the dangerous, exciting firsts, what is left for humans? Do we become mere passengers, or worse, armchair observers, watching the universe unfold on a high-definition screen from the comfort of our increasingly automated homes? There's a visceral, almost spiritual component to human exploration, to personally experiencing the unknown, that might be lost if our primary interface with the cosmos is through the emotionless sensors of a machine, however intelligent. Will we still feel that profound sense of wonder, that connection to the universe, if our robotic emissaries are the ones having all the aha moments while we just get the data dump afterwards? Furthermore, consider the companionship aspect. While a diligent robot that doesn't complain about your taste in music might sound appealing for a long space voyage, there's also the potential for a profound, almost cosmic loneliness if our primary interactions beyond Earth are with machines, however sophisticated. The universe is already vast and seemingly empty of sentient chatter. Replacing potential human colleagues with purely logical, unemotional AI might just amplify that sense of isolation for any humans involved. Hal, play me a song. I'm sorry, Dave, that activity is not mission critical and expends valuable energy resources. Would you like me to recalibrate the atmospheric scrubbers instead? So, as you allow your thoughts to drift on the quiet hum of imagined servo motors and the flicker of processing lights, contemplate these tireless electronic explorers. Marvel at their potential, their ability to go where we cannot, to endure what we cannot. They are a testament to our ingenuity, our drive to understand the universe even through proxies. But also, spare a thought for the subtle complexities they introduce, the questions of control, of purpose, of what it means to explore when the explorer is no longer human. Let the cold logic and diligent charting of these future AI companions provide a strange sort of comfort, a sense of order in the vast chaos. But perhaps also a gentle reminder of the unique, messy, wonderfully illogical spark of human consciousness, a spark that, for all its flaws, still yearns to see the universe with its own eyes. And with that, drift deeper into the serene, starlit peace. Our cosmic journey, having touched upon the brilliance of advanced AI and robotics, now brings us to a concept that is perhaps less about whiz-bang new engines or sentient computers, and more about good old-fashioned, if extraterrestrially located, resourcefulness. In-Situ Resource Utilization, or ISRU. It's a rather dry, technical-sounding term, but what it boils down to is something profoundly transformative, and perhaps even a little bit desperate. Learning to live off the land even when that land is a barren, airless, and generally inhospitable alien world. It's the gritty glamour of trying to make a home in the void, because nothing quite says intrepid space pioneer like attempting to extract breathable air from a toxic, lifeless rock and triumphantly calling it progress, all while secretly wishing for a decent cup of real, earth-grown coffee. Current status: missions are entirely dependent on resources brought from Earth. This is the fundamental challenge that ISRU seeks to address. Every mission, whether robotic or crewed, is essentially a cosmic camping trip where you have to pack everything. Your food, your water, your air, your fuel for the return journey, your spare parts, your entertainment. Hope you like freeze-dried ice cream and reruns of old sitcoms. This makes missions incredibly expensive due to the sheer mass that needs to be launched out of Earth's deep gravity well. It also limits their duration and scope. You can only stay as long as your packed supplies last. It's like trying to establish a permanent settlement in Antarctica but insisting that every single ice cube for your drink has to be flown in from the equator. The future prediction and the change it promises are revolutionary. The ability to mine water ice on the Moon or Mars to create rocket fuel, oxygen, drinking water, mining minerals for construction. This helps off-Earth bases become more self-sufficient, reducing the cost and complexity of long-term missions. Imagine a lunar base where astronauts aren't constantly rationing water shipped from Earth at astronomical cost, but are instead drinking water extracted from ice deposits found in permanently shadowed craters near the lunar poles. Imagine a Mars mission where the ascent vehicle isn't pre-fueled for the return journey with propellant laboriously hauled all the way from Earth, but instead tanks up with methane and oxygen produced on the Martian surface using atmospheric carbon dioxide and subsurface water ice. This is the promise of ISRU. The technologies involved are varied and complex. For water ice, you might use robotic excavators to dig up the icy regolith, then heat it in an oven to release the water vapor, which is then collected and purified. This water can be used for drinking, for growing plants in hydroponic labs, fresh space salads, anyone? For radiation shielding, or it can be split through electrolysis into hydrogen and oxygen. The oxygen is obviously useful for breathing, but both hydrogen and oxygen are powerful rocket propellants. Suddenly, the Moon or Mars isn't just a destination. It's a potential refueling station, a cosmic gas station on the interplanetary highway. Your Mars mission suddenly becomes much more feasible if you know you can make your own ride home. Other ISRU concepts include extracting metals like aluminum or iron from lunar regolith to be used as feedstock for 3D printers, creating tools, spare parts, or even structural components for habitats. The regolith itself, that fine abrasive dust that covers the Moon and Mars, could be sintered or mixed with binders to create lunar concrete for constructing landing pads, roads, or radiation shielding berms. It's about turning the hostile alien environment from a liability into an asset, albeit a rather challenging one to exploit. The sleepy angle here is turning alien worlds into sources of life, human ingenuity, and adaptation. There's a certain romantic, pioneering grit to this. It harks back to the spirit of early settlers on Earth, learning to make do with what the local environment provided, however harsh. It's a testament to human adaptability, our stubborn refusal to be constrained by our origins. We're not just visiting these other worlds, we're trying to live there, to put down roots, however tenuous. There's a deep, almost primal satisfaction in the idea of coaxing life-sustaining resources from a seemingly dead rock. But let's not get carried away with visions of idyllic Martian farms and bustling lunar mining operations just yet. The gritty glamour also comes with a very large dose of, well, grit and dust. Lots and lots of incredibly fine, abrasive, electrostatically charged, and potentially toxic dust. Lunar regolith, for example, is made of tiny razor-sharp particles that get into everything: spacesuits, equipment, lungs. It's a constant maintenance headache and a potential health hazard. Mars dust, while perhaps less abrasive, is pervasive and contains perchlorates, which are not exactly health food. Sipping filtered regolith, as our Rye note puts it, might be technically feasible after extensive processing, but it's unlikely to win any Michelin stars. And you'd better hope your filtration system is top-notch, otherwise your water source might come with some rather unwelcome chemical surprises. The energy requirements for ISRU processes are also substantial. Mining, hauling, heating, electrolyzing, these are energy-intensive activities. You'd need robust power sources, likely solar arrays, which get covered in dust and are less effective further from the sun or during planetary night/dust storms, or compact nuclear reactors with all their attendant complexities as we've discussed. The machinery itself needs to be incredibly reliable and preferably capable of autonomous operation or remote repair, because sending a mechanic to Mars is not a quick fix. And then there's the sheer uncertainty. We have good evidence for water ice on the Moon and Mars, but its exact distribution, concentration, and accessibility are still being mapped. What looks like a rich deposit from orbit might turn out to be disappointingly sparse or difficult to extract once you get your robotic shovel on the ground. Early ISRU efforts will be experimental, high-risk, and probably involve a lot of frustrating trial and error. Houston, the regolith to rocket fuel converter appears to be producing something that smells suspiciously like burnt toast and despair. Requesting permission to revert to Plan B, which currently involves a very long walk. So, as you let your mind settle into a state of deep relaxation, picture those first ISRU pioneers, human or robotic, diligently working away on a distant, dusty plain. There's a profound sense of hope in their endeavors, a vision of a future where humanity is no longer tethered to a single world. But there's also a stark appreciation for the immense challenges, the sheer, stubborn difficulty of coaxing sustenance from an alien landscape. It's a story of ingenuity and perseverance, but also one that reminds us of the preciousness and unique bounty of our own Earth. For all our dreams of cosmic homesteading, there's still no place quite like home, especially if home has readily available, non-toxic coffee. Let that thought, a blend of audacious hope and earthy pragmatism, guide you into a peaceful, restorative sleep. As our cosmic journey through humanity's technological leaps nears its gentle conclusion for this particular sleepy excursion, we find ourselves drifting away from specific inventions and towards a more contemplative, perhaps even slightly melancholic, observation. We've marveled at the fire of rockets, the silent logic of guidance systems, the versatile ambition of shuttles, the far-seeing eyes of space telescopes, the patient efficiency of ion drives, the elegant dance of solar sails, the tireless diligence of AI explorers, and the gritty resourcefulness of in-situ utilization. And yet, underlying all these magnificent achievements, all this striving and ingenuity, is a fundamental, often unstated truth. We, the creators and operators of these wonders, are remarkably fragile beings, venturing into an environment that is, to put it mildly, not designed for our comfort or survival. We are, in essence, soft, remarkably squishy creatures in extraordinarily dangerous metal cans, a profound and perhaps rather inconvenient truth that the universe, in its vast starlit indifference, finds deeply, deeply uninteresting. Think about it. The human body is a marvel of biological engineering, perfectly adapted for the relatively benign conditions of planet Earth. We thrive within a narrow range of temperatures, require a specific atmospheric pressure and composition, are dependent on a constant supply of liquid water, and are rather vulnerable to things like radiation, hard vacuums, and sudden, extreme acceleration. Take away any of these terrestrial comforts and we fare very poorly very quickly. Space, on the other hand, offers none of these. It is, by its very nature, hostile to unprotected life as we know it. It's too cold or too hot. It's a vacuum. It's bathed in radiation from the sun and from distant cosmic sources. It's littered with micrometeoroids traveling at bullet-like speeds. It's really not a great place for a picnic, unless your idea of a good time involves explosive decompression and a rapid, unceremonious freeze-drying. So what do? We build cans. Very sophisticated, very expensive, and hopefully very reliable cans. Spaceships, space stations, spacesuits, these are all, at their core, attempts to recreate a tiny, fragile bubble of Earth-like environment in the midst of an alien wasteland. We meticulously manage the air pressure, scrub the carbon dioxide, recycle the water, yes, including that water, try not to think about it too much before bedtime, shield against radiation as best we can, and try to keep the temperature within a range that doesn't result in either hypothermia or spontaneous combustion. It's an ongoing, relentless battle against the fundamental nature of the universe outside our thin, metallic shells. The sleepy angle here is a gentle, sleepy reminder of this inherent fragility, not to induce anxiety, but to foster a sense of profound appreciation for the delicate balance that sustains us, both on Earth and in our tentative forays beyond. It's a humbling perspective. We may dream of conquering space, of becoming a multiplanetary species, but we are always doing so as vulnerable, biological beings, utterly dependent on our technology to keep the indifferent hostility of the cosmos at bay. Our grandest voyages are, in a way, a testament to our ability to trick physics, or at least to temporarily hold its more lethal consequences in abeyance through clever engineering. Consider the astronaut in their spacesuit, performing an EVA, an extravehicular activity. They are, for all intents and purposes, a tiny independent spacecraft. Their suit provides pressure, oxygen, temperature control, communication, and some measure of protection against micrometeoroids and radiation. It is a marvel of miniaturized life support. But it is also a constant reminder of the lethality just millimeters away. A tear in the suit, a malfunction in the oxygen supply, and the universe reclaims its territory with swift, impersonal efficiency. It makes that slightly stuffy office you work in or that drafty bedroom seem positively luxurious by comparison, doesn't it? And even inside the relative safety of a spacecraft or space station, the challenges are immense. Prolonged exposure to microgravity wreaks havoc on the human body. Bones lose density, muscles atrophy, fluids shift, the immune system can become compromised. Cosmic radiation subtly damages DNA, increasing the risk of cancer and other long-term health problems. The psychological toll of confinement, isolation, and the constant awareness of being so far from home, in such a perilous environment, cannot be understated. Astronauts are selected for their resilience, their training, their mental fortitude, but they are still human. They still miss fresh food, the smell of rain, the feeling of wind on their skin, the simple comfort of knowing that a vast, life-sustaining biosphere is just outside their door, rather than a cold, unforgiving vacuum. This is not to diminish the heroism or the achievements of space exploration. Quite the contrary. It is to highlight the extraordinary courage and dedication required to venture into such an environment. It's to marvel at the ingenuity that allows us to survive, even thrive for limited periods, where we so clearly do not belong. But it's also to acknowledge, with a sense of wry realism, our fundamental biological limitations. We are creatures of Earth, adapted for Earth. Our ventures into space are, in many ways, an act of profound defiance against our own nature, a testament to the power of the human mind to overcome the limitations of the human body, at least for a while, and with a great deal of technological assistance. The universe, as we've noted, isn't actively trying to kill us. It simply doesn't care. It operates according to vast, impersonal physical laws, and we are just tiny, complex chemical reactions that have, for a brief cosmic moment, achieved self-awareness and a rather inexplicable desire to go poke around in the dangerous bits. This cosmic indifference can be unsettling, or it can be strangely liberating. It means there's no cosmic malice directed our way, but also no special protection. We are on our own, armed with our wits, our tools, and our fragile, precious lives. So, as you sink deeper into the soft embrace of your bed, into the comforting familiarity of your own terrestrial environment, spare a thought for those fragile shells carrying our hopes and dreams through the cosmic night. Appreciate the air you breathe so effortlessly, the gravity that holds you gently to your mattress, the planetary magnetic field that shields you from the worst of the sun's temper tantrums. These are gifts of Earth, gifts we must painstakingly recreate at enormous effort whenever we venture beyond its embrace. And in that appreciation, perhaps find a deeper sense of peace, a quiet gratitude for the small, blue, improbably hospitable corner of the universe we call home. Our journeys to the stars are magnificent, but so too is the incredible, life-sustaining miracle beneath our feet. Let that thought cradle you into a profound and restful sleep. And so, our sleepy journey through the technological marvels and occasional magnificent blunders of aerospace draws to a gentle, contemplative close for tonight. We've soared on pillars of fire from Goddard's early, hopeful explosions to the thunderous majesty of the Saturn V. We've trusted our fate to the silent, spinning gyroscopes and the blinking lights of primitive but heroic computers. We've witnessed the flawed, expensive ballet of the shuttle, a dream of reusability that taught us hard lessons. We've gazed through Hubble's corrected eye and Webb's infrared lens into the staggering depths of cosmic beauty and our own profound solitude. We've contemplated falling rockets and rising debris clouds, the ingenious promise of cosmic 3D printing, the slow burn of nuclear hopes and the patient sigh of ion drives. We've dreamt of sailing on sunlight, wary of cosmic pigeons, and considered the cold logic of AI explorers charting empty frontiers. We've even imagined sipping filtered regolith, all in the name of progress. And through it all, we've been reminded of our own fragile, squishy nature, tiny beings in dangerous metal cans, venturing boldly where we are not naturally equipped to survive. Now, as we prepare to let these thoughts dissolve into the quiet currents of genuine sleep, we arrive at a final, overarching reflection. This grand, absurd, and utterly human ascent towards what exactly? Humanity's relentless technological climb towards the stars, this beautiful, perhaps inspiring, and quite possibly, from a purely cosmic perspective, utterly pointless endeavor in a universe that is mostly empty, demonstrably indifferent, and definitely doesn't return our enthusiastic and often rather loud calls. Consider the sheer, almost manic, energy we pour into this. The billions upon billions of dollars, yen, euros, rubles. The countless hours of human ingenuity, the lifetimes of dedication from scientists, engineers, technicians, and astronauts. The risks taken, the sacrifices made. All to push a little further, to see a little clearer, to understand a little more about this vast, silent stage upon which our brief, noisy drama unfolds. From one perspective, it's the noblest expression of the human spirit, that insatiable curiosity, that drive to explore, to transcend our limitations, to reach for something beyond ourselves. It's in our nature, perhaps hardwired into our primate brains that once looked up from the savannah and wondered what those twinkling lights were. From another, slightly more jaded and perhaps more cosmically aligned perspective, it can seem like a rather peculiar obsession. The universe, as far as we can tell, was getting on perfectly fine without us knowing the precise composition of Martian soil or the redshift of the earliest galaxies. It has existed for nearly 14 billion years, churning out stars and galaxies, black holes and nebulae, all with a sublime disregard for whether or not a small, carbon-based species on a minor planet in an unexceptional spiral galaxy was taking notes. Our grandest discoveries, our most profound insights, are, to the universe at large, less than a whisper in a hurricane. And what is the ultimate goal? To find life elsewhere? A noble pursuit, certainly, one that could reshape our understanding of our place in the cosmos. But what if we find it, and it's either microbial and uncommunicative, or so vastly different, so incomprehensibly alien, that meaningful interaction is impossible? Or worse, what if they're just not that into us? Oh, them, a hypothetical advanced alien might observe with a cosmic sigh, the noisy ones from Sol 3 who keep launching pointy things. Best to just keep the "do not disturb" sign lit. Is it to ensure the long-term survival of humanity by becoming a multi-planetary species? A prudent goal, perhaps, given our talent for messing up our home planet and the universe's occasional penchant for throwing large rocks our way. But colonizing Mars or the Moon, truly making them self-sufficient outposts, is a task of such monumental difficulty and expense that it makes all our previous space endeavors look like a gentle stroll in the park. And even if we succeed, are we just exporting our problems, our squabbles, our capacity for self-destruction, to new and initially pristine celestial bodies? The universe has seen empires rise and fall on a cosmic scale. One more fledgling interstellar civilization, however ambitious, is unlikely to make a huge splash in the grand scheme of things. This isn't to say it's all meaningless. Far from it. The meaning, perhaps, is not in some grand cosmic validation but in the striving itself. In the knowledge gained, in the technology developed, much of which has profound benefits right here on Earth, in the international cooperation often fostered, in the sheer, breathtaking audacity of the attempt. It's in the way these endeavors can inspire us, can lift our gaze from our immediate, terrestrial squabbles and remind us that we are part of something much, much larger, even if that larger something doesn't particularly acknowledge our membership. There's a profound, almost tragicomic beauty in our cosmic aspirations. We are like children building increasingly elaborate sandcastles on the edge of an infinite, indifferent ocean, knowing the tide will eventually come in, but building them anyway with passion and dedication, for the sheer joy and challenge of creation. Our rockets are our defiant shouts into the void, our telescopes are hopeful glances into the unknown. And the universe, in its silent majesty, simply continues its eternal, unhurried dance, occasionally providing a spectacular backdrop for our fleeting efforts. So, as we conclude this sleepy history, this gentle poke at the underbelly of our grandest dreams, let this final thought settle. Our journey to the stars is a magnificent folly, a glorious absurdity, a testament to the strange, wonderful, and occasionally self-destructive creature that is humanity. It's full of triumphs and tragedies, brilliant insights and spectacular miscalculations. And it is, above all, profoundly human. And perhaps in a universe that often feels cold and indifferent, that very humanness, that stubborn, hopeful striving, is the most meaningful thing of all. It may not change the universe, but it undoubtedly changes us. And with that thought, a thought that hopefully brings a wry smile and a sense of peaceful acceptance of our wonderfully absurd place in the cosmos, allow yourself to drift completely. So, little star voyager, your mental journey through the bright sparks and dark voids of aerospace history is complete for tonight. The rockets have all landed or spectacularly haven't. The telescopes are patiently gathering light from epochs long past. The AI is calculating trajectories to places you'll only visit in dreams. And you are here, safe and sound, on your terrestrial bed, a vessel of flesh and bone that has just traversed billions of dollars of innovation and eons of cosmic time, all without moving a muscle. Quite efficient, really. Remember, as you drift into the deepest, most restorative layers of sleep, that while the universe is a canvas of breathtaking beauty, it's also a vast, churning machine full of extremes that would snuff out your little spark in an instant. It's got the explosive power of a billion suns, the coldness of absolute zero, the crushing gravity of black holes, and an attention span for human endeavors that is, frankly, negligible. It's not personal, it's just physics on a scale that makes our entire existence look like a rounding error in its grand, terrifyingly beautiful equation. But tonight, in the soft haven of your mind, in the gentle cocoon of your blankets, none of that magnificent, indifferent chaos can touch you. The worries of your world, so large in the daylight, now shrink to tiny, distant stars against the backdrop of cosmic immensity. The universe will continue its silent, grand ballet, indifferent to your slumber. And that's okay, because here in this moment you are at peace. Let the gentle pull of sleep be your gravity now, anchoring you to dreams where anything is possible, where even the starkest truths of the cosmos can become a source of quiet wonder, and perhaps a sleepy, knowing chuckle. Sweet dreams. You've certainly earned them, navigating all that cosmic irony. Go on now, sleep.